Okay, well, good afternoon. Welcome to our webinar here on the water loss determination and management programs. Here we're putting it on as a committee here at the AZ Water Energy and Sustainability Committee. My name is Noah Munt. I am the moderator, as well as I'm presenting a short synopsis of our last session that we did. So much like the Hair Club for Men, I'm also a client. If you're interested in becoming a member, of course, the committee, please visit the AZ Water Association's homepage at www.azwater.org. You can click on the committees link at the top of the homepage and select the committees that you find of interest. Before we begin this webinar, I have a few housekeeping notes. If you have questions for the speakers about the presentations, please type them into the question or chat window in the GoToWebinar control panel displayed on your screen. A short question and answer session will be held at the end of this if time permits. The professional development hours for this will be approximately 1.5 to 2, depending on the time. A certificate for this webinar will be available as a handout following. If you would like one, please just email me. My email is noah.munt@siemens.com. You can also find that in the ad for this, and I think everyone should have that. And if for some reason you're unable to get it, like I said, just give me a call and we'll coordinate that. So for our presentations, we have 4 different presentations, and we're going to kick it off just with a short review and some discussions on what exactly these non-revenue water programs look like, whether it goes to leak detection, supply side, demand side management, and those types of things. And then we have 3 other presentations that we will get into, and I will introduce you to those presenters at that time. So to get started here, this is about water loss determination and management. We had done a recording back in November where we had a discussion of the AWWA's M36 protocol related to finding leaks or non-revenued water within a water distribution network. So if you think about it, let me get through that, I apologize. So the M36 goes on water audits and loss control programs. This is sort of a first step in determining if we have a problem. So a water district may produce so much water, then send so much out. You have billings. Sometimes within that, there is a disconnect on exactly how much of that water is actually being accounted for. And there are certain programs that states use. A certain number of states like California, Texas, and several others use what this M36 protocol. And there's been some movement in possibly trying to push this through as something that Arizona could use and other states here in the Southwest. So when you look at this, you come up with a balance of the actual amount of water that you put into your system. So when you take water out of the ground, whether it be from wells or surface water, you put it through your treatment, and then from there you send it out. You probably have some meters on both your well pumps, your booster pumps, as well as the booster pumps that send the water out of your plants. And then at the end line, you have a specific amount of water that actually is accounted for at the end line of your users, whether that be commercial or residential metering. And anything that does not account for that is considered non-revenue water. So there's a very different variation. As you can see, there's a couple of different metrics, whether it is unbilled or unauthorized consumption. These are in older networks. You sometimes just have water lines that lead up to businesses, houses, parks that there's never was a meter put on. And then there's also some that have meters, but it's just not billable meters. This could be fire stations, libraries, anything possibly within a municipal organization that you just have some kind of a agreement on water usage. Then you have an apparent loss. So these are unauthorized consumption or meter inaccuracies. Unauthorized consumption could be people tapping in or utilizing water that they aren't actually paying for, nor they have an account. And the meter accuracies deal in if you have a meter that's 80% accurate, in essence, you're giving away 20% of the water that pours through that. So that's a very simple way of describing it. And then there's the real losses, which deals in transmission line leaks, storage leaks, and service connection leaks at the meter. So when you think of water loss and leakage, more often than not, you think a lot about these real losses, and that's what we're going to dig into quite a bit today. But I want to give a short synopsis on what customer meter inaccuracies can possibly do and what fixing those looks like. So on your path to figuring out how to deal with water loss as a whole, you first, of course, on the top side, look at, well, what do I have? What's going on? What are my percentages? Then you can do some mapping and leak detection. So at the top side of the inflection point there is where we're going to discuss today. Then you can look at your meters, DMA, SCADA systems, district, depending on the district size, district metering, pressure management, long-term asset management, and of course, IoT data integration and visualization and those types of things. This is from Tata and Howard here. They have a nice, illustration where you see what leaks describe here. You can see small components of non-revenue water is in street sweeping, hydrant flushing, these things that municipal organizations always use, tank overflows, and then you get into billing errors, theft, and meter errors. So those meter errors and the production errors, this is a nice, I like to use this as an example of how putting a water balance program can look. This is actually in Manila, the Philippines, so not exactly a great representation of a strong municipal here in America, but you can see when they started back in the late 90s, they had non-revenue water near half that they were losing. And when they began to account for it, you can see how these curves, the number of connections increased, the amount of billed water, and that's of course in a metrics of millions of cubic meters. You can see where you start to meet the production and the build. So where those two blue and green lines meet at the end there is really as even as possible is where you want those to be. And as you remember from the last webinar, if you were on it, and you may not, but we can get you a copy if you want to look into it. We had AZDWR as well as the Corporation Commission discussing a program that they're currently putting out as a pilot to help municipal organizations outside of the active management areas here in Arizona to pursue this M36 protocol. And there should be a report on that coming out soon. And they just recently have put out a notice of bid looking to expand that from the initial pilot to a larger scale. I believe the first one went for 6 or 7 water districts, and they're going to be looking to do 25 in this next round, I think. So this is something that's gaining traction, and hence we wanted to talk about it a bit as an organization. So with that, I am now going to turn it over to Mike Simpson, where he is going to get into a little more depth about, okay, we've done our audit. Now what exactly are we supposed to do? So, Mike, I've just made you presenter, so take it away when you're ready.
Well, I get it to cooperate. Do you see the slides, Noah?
Not yet. Did you do show screen on the little play button on the top of the?
Show screen.
There it is.
Okay. All right. Well, good afternoon, everyone. It's a pleasure to be here and to talk to all of you about water loss control, and specifically talk about water audits and what do you do when you've got your audit done. And as we go through this, we kind of want to talk about all the different issues regarding completing your audit and then reviewing your audit and verifying its accuracy. And what we have here is we've got an example audit from a utility in Illinois, but I have changed the names to protect the innocent. But this was an audit that was completed last year regarding the 2016 fiscal year. for their water system. And as we go through this, we're going to talk about the specific areas of the audit and the water supplied, our authorized consumption, our water losses, both apparent and real. We're going to speak about non-revenue water specifically, talk about system data, and get into our cost data, talk about validity scores, and then talk about priority areas for your attention.
Hey, Mike, real quick, if you could, on the top of your screen, the display settings, just make that the full screen mode. In the top, to the left, more to the left. There you go. Let's see. It didn't go yet. Do you see where the display settings is on the top of there?
Display settings, sorry.
No, no worries. There you go. Yeah, click that.
Did that work?
Yep, you're good.
Okay. All right, sorry about that. So anyway, we go through these areas, and we want to look, at each of these areas and kind of pick them apart, so we have a good indication of what's happening in our system. And as you can see here, we have our water supplied. The utility buys all their water from an agency. So they had a confidence level of the information they received from that agency of a 6. They felt the meters were only inaccurate, but they really didn't know. So they just, in this case, gave their best guesstimate that it would only be off by 1%. When we filled out our authorized consumption, you can see that that was an 8, because that's their billing system and their system. They're unbilled metered. They had great confidence in. That's their city facilities. And then they're unbilled, unmetered, that areas that they don't control. And they walk through each of these specific areas. So we talked about our water supplied. We looked at the authorized consumption. We look at our water losses, and we're losing 238 million gallons in a year, which gives us a real loss of which is the current annual real losses of 190 million gallons a year. So a closer look is, we want to get into the system data that's a part of this. And so this goes to your GIS system, to the information you have in all your records. So you need to know the length of your water mains. In this case, 292.6 miles. They had strong confidence. They gave themselves an 8. Number of active and inactive services, they felt confident about this number. And so their service connection density was about 80 connections per mile. Since this is the Midwest and the Chicago metro area, the water meters are in the house. So the service line length is much longer because it goes beyond the property boundary. It goes into the house. You can see their cost data. What it costs them to run the utility for the year, and that's their operating utility, and they're purchasing water. The cost of water to a customer averages $10.25 per 1,000 gallons. Their production cost is $5,300 per million gallons for what they purchase it for. You remember that all your system data and cost data is used to calculate your performance indicators. This information is very important to, your overall audit and your score. So as you go through this and you look at the non-revenue water as a percentage, they're losing 9.7% of their of the water that they purchase and they don't sell to someone, and it gives them an infrastructure leakage index of 1.13. Now that's the audit as they did it and all the data they provided. We took the audit and redid it, and we reviewed all the information they provided, and we gathered more data from their systems, and we reviewed all their validity scores, because in reality, when you do this is where all the problems come in. You can fill that spreadsheet out in about 15 minutes, unless you actually take the time and effort to gather all the data and information that's required in each section, and you actually review that data to make sure the data is accurate and the information you have is accurate. I think everybody understands, you've been talking about it in these different seminars. You know, the water balance format is pretty simple, it's pretty straightforward. We have our own sources or water you purchase. You've got the total system input. We're moving in this direction. So any water you sell to another agency or municipality, the water you supply to your system, what's authorized, and next becomes your losses. And then what you've billed authorized, any unbilled authorized, and then we get into our apparent and real losses, which create our non-revenue water. And it breaks down from there in the matrix to individual components that as you fill this out and complete all your data, you'll see it on your spreadsheet. For our community here, you can see where they imported the 2.8 billion gallons of water. That's what they supplied into the system. And then the authorized was the 2.5 billion was authorized or went through customer meters, but 238 million did not. And then as we see, we break it down into each of its individual pieces on apparent losses versus real losses, and then broken down farther as you go through the matrix. You can see what each area where problems are, or where things where they track stuff. And as you can see on their leakage end of it, on their real losses, they did not have any breakdowns. They did not keep as good a records on that information, what's happening in their real losses. So you start there and you move that direction as you pick it apart and as you fill the data out. Again, the concern on this one, a practice that they're now changing in their system, is tracking their real losses and what's happening when they have water main breaks and they find leaks and everything else when they do leak surveys. But all this goes to their real losses of 190 million gallons a year. So the first thing we did is we reviewed the water supply data, and we looked through all that data to compare it against our validity scores and our end answer. And as I said in the beginning, this is really about how you finish your audit. And this is about how you make sure you validate what you've done or what somebody else on your team has done to ensure that you've got the right answer. One thing I want to point out, we pointed out that the validity or the infrastructure leakage index was a 1.13. That is an exceptional score, something that you can be really proud of. But I can tell you that that's not something that you take lightly. And so that end score is how you start the audit. And so the big question becomes, if the water supplied information is wrong, then the bottom answer is going to be wrong too, and your whole audit's going to be wrong. And that's one of the first places we look when we validate and review audits, and when we do audits for utilities, is we look at treated water meters, or in this case, the wholesale water meters, who you purchase from, your total finished water, what you delivered, anything that you sold. But as Noah mentioned in the beginning, and he was focusing a little bit on the apparent losses on the commercial, industrial, and your residential side, one of the first areas is the water meters that put the water into your system. Because again, if you don't put the right information in, the right information doesn't come out at the end. So in the first part of the audit form, they chose a 1% inaccuracy, and they gave it a validity score of 4, which told all of us they didn't know for sure what the meter accuracies were. So how much water really went into the distribution system? So went back and tested all 4 wholesale meters at their 4 locations to determine the true volume of water being introduced into the distribution system. This was critical, testing those meters, and let me advise everyone or comment to everyone that in the case of production or master meters at your facilities, testing the 4 to 20 milliamp signal between the head of the meter and your SCADA board or your computer is not a meter test. It's certainly important test of the signal between those 2 items and that it's transferring correctly, but it had nothing to do with the water meter and its accuracy. So when the meter testing was complete, we found that the meters between the 4 meters had an average inaccuracy of 9.62%. So the water supplied into the system was actually 3 billion gallons. It was not the number they first thought. They thought it was 2.8. It was really 3 billion gallons. That has a huge effect on the overall accuracy of this program and of this audit. The difference between the actual inaccuracy of the meters versus what somebody surmised. How does this affect the audit result? Well, we look at our original and we compare it against one another. Oops, sorry, went too fast. You can see the differences in apparent losses, in real losses. These are significant number changes by introducing the correct amount of water that was introduced into the system. So this has a huge effect, both in total volume of water, a huge financial effect, and a huge effect on your percentage of losses as you look at the whole thing. Everything basically, in essence, better than doubled. So their infrastructure leakage index, where they were almost what was considered perfect, has now gone to what is considered normal. As I've done all these audits and done this stuff over the last 35 years of my career, I can tell you there are no real perfect water systems out there, and knowing that is an important thing. And though we all want to strive for perfection, we need to focus on reality and not what we desire to be. So our current annual real losses jumped to 341 million, which tells us that our unavoidable annual real losses are 142 million, and that's how we get our ILI at a 2.40. Simply put, water loss leakage is calculated by the leakage index is essentially double than what the original audit said. Fixing that number changes the physical characteristics of the water system, changes everything. By increasing the total system input, and not changing anything else, your water loss is going to go up. So this is helping you, and as we go farther in this webinar and we get to the next speakers, they're going to talk about the different things you can do in your system to then mitigate the losses that the audit finds. So we've revised our input, which is changed our annual water loss by revising our input. And what it's really done is it's told us what our cost of our apparent losses and our real losses are costing us. So this is going to help in the directions we need to move forward in our systems. And again, others are going to talk about going farther forward, what we can do to bring these numbers down or recover that revenue, because that non-revenue water is sitting out there. And of course, it has an effect. If you want to look at it from a percentage basis, it has a huge effect from a percentage basis. So, you know, and this is something that everybody strives to bring those numbers down. And again, then your current annual real losses, again, you're talking about almost doubling. And, you know, these are the kind of things that you've got to check. An example, you know, is it possible to have a meter operated at 150% accuracy when the certified report says it's 99.5% accurate? Well, if you've got everything jammed together and you create this type of flow and you've got a distance between your meter and your check valve of 24 inches, that meter's going to overspeed because you're going to create a jetting action on the bottom of that water meter. And this is one of the things that has a huge effect that we find in systems. In this case, your water loss isn't as bad as you think, but it's worse if you're putting in accuracy limits that are lower than what's really happening. So, you know, all those things come into play. That's why meter testing is so invaluable. Actual information provided is so invaluable when you're doing these type of programs and when you're doing your audit. You know, again, the information in your audit is only as good as the data you put into it and the effort you make. Straight line of pipes provide ideal flow. If you read the M6 manual, it will tell you exactly how to distance things from upstream and downstream from your water meter to make it operate correctly. And actually all the meter manufacturers, their installation guides will tell you the same thing. You know, some items not changed with the revised audit. You know, the authorized consumption, that was accurate, that stayed the same. You know, the unbilled unmetered was an actual estimated amount was used instead of the default value. They used the default value in the beginning. They went back and tracked a lot of the activities that were done and put in an actual amount to make it more reflect a more accurate value. In the apparent losses, again, went back, reviewed all the practices, reviewed all the meter testing data that they had over a 2-year period of time, and realized in their customer metering side, their average inaccuracy was 5%, not the 1.3% that they first put down, which gets into the apparent side that the others will talk about. That's very important when you're talking about revenue for your system, because if the meters are inaccurate, you're losing money. System data, the miles of pipe, there was some inaccuracies in that. There was a mistake in the GIS. Those were all corrected to get a true accuracy. There was also an issue with the number of service connections. Again, inaccurate data. Had to go back and research everything and research through the data, and also check the averages of the PSI and pressure is an important part of leakage, and found a more accurate PSI for the study. all these adjustments will have a big effect on the URL. Everybody, I hope understands URL. It's, the theoretical reference value representing the technical low limit of leakage that could be achieved, and all of today's best technology could be applied to a water system. Leaks that you're never going to find. The URL is calculated in gallons per day, and where length of mains, number of customer services, the average distance of a customer service, the total length times the miles with the pressure gives you, times the pressure will give you your answer. Background leakage that cannot really be found. And in some cases, I think everybody here understands that in reality, there are some leaks because of their just size, it is not cost effective to fix. A half gallon a minute a leak on a joint on a 12-inch main in the middle of the busiest intersection in town probably is not going to be a huge priority, because financially it would be a disaster to dig that up to do that. So, as you see, any change of these numbers have an effect on the URL, and all those things had to be changed after the audit was validated. So as we walk through again with the numbers, you can see again, that our unavoidable real annual loss changed, and it had a direct effect on our infrastructure leakage index. And that is important. So we measure ourselves in a metric where we can see where we're at. All the system data changes had an effect on that. Accounting for the differences in the numbers, the GIS data identified private water mains, shopping malls, strip malls, HOAs, condo associations, and community college campuses that no one was accounting for. No one accounted for that amount of water main. That's how that all got added in to increase the amount of water main in the system. The GIS also identified Siamese connections for HOAs and condos. So that changed the number of services. That information was found in the GIS data and helped make that change. The consequence of those private water mains that are unmetered and belong to the shopping mall or the college campus or the condo association, leaks can occur and go unnoticed, and they're unmetered. There's no real incentive for an owner to perform any pipe maintenance until the leak becomes noticeable or huge because it breaks. The utility is absorbing the costs of that lost water. I know a lot of normal municipal systems have private mains and sections that are not a part of their system that's unmetered. And this, it's got to be, it includes fire loops, some of these gated communities, and in commercial industrial sectors where factories loop their building with fire hydrants. All that stuff can go unmetered, and if it's leaking, it's costing you money. We look at our ILI, that's our real losses, will get us down to our where our ILI is and what our current annual real loss is. And this is an important number because our real losses, are the leakage, and how can we capture some of that back? The infrastructure leakage index is the ratio of current annual real losses divided by the unavoidable annual real losses. In theory, an index ratio cannot be lower than a 1. A 1 would indicate a perfect water system. The members of this committee, which I sat on for a decade, worked really hard on all this, and I think we're on the fifth version of the auditing software, and all the data gathered from across the world to create this software and these matrices. We've yet to find a system that's a 1 unless somebody makes it that, and then we refer to that as your fibbing. So you can find this right in the water audit software, which I failed to mention you can get from the awwa.org, the Water Loss Control Committee page. It's free, it's for everybody, it's for anyone's use. All this information is contained in there on what you should be. But our water system in Illinois falls in the 1 to 3.0 range. Whoops, too fast. Excuse me, falls in the 1.30 range, so it's in a good range. They do a lot of really good things and do a lot of things financially, operationally, and through their resources well. But there's still more that can be done. So the audit dashboard will help you because it gives you all kinds of information that you, the operator, can use while tracking your system and seeing what's happening. It gives you dashboards to tell you about your water, and your non-revenue waters and the areas that that are causing you the most angst or problems. And in the case here, our biggest issue by volume is our real losses, and that's a by volume. If we do it by cost, all of a sudden the apparent losses who did not lose as much on the volume side, but it cost us a great deal of money, though real losses is still costing us more. Validity scores, this is the part that you as the professional doing this, the water professional doing this audit, this is the part where you've got to be honest with yourself. If you don't know the answer to the question or you're not confident in the answer, then give it the correct score. You can see here we rate it from 1 to 10, and I can tell you that if you don't have a sound policy, you need to be marking things with a 4 or less. If you don't have procedures to document or do this kind of information, this is what you need to do. This was what happened with the water mains, with the service connections. They shouldn't have given themselves such high marks because they didn't research the data and they didn't look in the right places. Just because you have a GIS system doesn't mean that you give yourself a 10 or a 9. And the same even goes with an AMI system and your meter reading and billing systems. Just because you have it, how are you implementing? How is it being tracked? How is it being done? Also plays into this. I had a system that when I audited the system, I got 3 different answers on how many miles of water main they had and how many service connections they had from 3 different groups. So that's a classic example of what can go wrong in an audit and how it gives you the wrong score, the wrong information, and leads you down the wrong path. You need to put down the correct information, and if you know the correct information, then you give yourself the correct answer. This is hard to read, and it's probably hard to read on the screen unless you blow it up, but to qualify for a 10, you've got to maintain annual meter, records. You have to do all kinds of things. This grading matrix has lots of pages of grades and will tell you lots of information on how to go through and actually grade yourself and grade yourself correctly. To qualify for a 10, maintaining, meter accuracy, testing, repair, replace outside meters of a plus or minus 3% accuracy. It is a tough nut to crack to get to that level, a tough nut. So when we talk about apparent losses, this is an important area in the reporting worksheet. We look at this money, and that's the biggest thing is the money, and how can we recover that 1.5 million? How do we get that back into our pocket? And that's through testing programs, new AMI systems. So you look at your 4 pillars of apparent loss management: meter accuracy errors, data transfer errors, data analysis errors between things, unauthorized consumption, theft of service, These are all things that you've got to put into play when you're going through your audit and how you move your audit forward. You've done it, you've corrected it, you know your answers are right. Now how are you going to move forward so that your non-revenue water management team, is making sure that billing and reading and customer service and revenues and field services all are doing their jobs to make sure you're collecting every nickel you can. Controlling apparent losses, measurement technology, accurate customer meters, refined data logging, AMR, improving information management systems for customer billing, AMIs, good rational policies. And then also looking at your service provisions and your unauthorized consumptions and your billing procedures and your use of hydrants, making sure stuff isn't getting away from you. Your meter's your cash register. It's the one of the most important parts of the system and the most important parts to you. I can't emphasize that enough, how you've got to pay attention to your meters. But again, the beginning meter is what you have to pay attention to the most. Your billed metered consumption, gives you, tells you what your annual apparent losses are. And and then you compare that to what your meters cost or what your water costs, gives you your cost of water. So your meter management gets into your reading and billing, your testing and maintenance, your replacement, and your meter selection and your installation. The proper installation following the guides of AWWA's M6 as well as following the manufacturer's installation is critical to making sure that meter runs accurately and gives you your value. In this audit, we looked at meters by type, size, age, and use, and the commercial customers represented 10% of the total number of meters, but 56% of the total water used. Obviously, the residential side was 90% of the meters, but they represented 44% of the water used. The largest recorded use in the commercial meter was seen in a 2-inch, and the largest residential was in a 5/8-inch meter. So it just isn't also always based on the size of the water meter. Just because it's a 6-inch meter doesn't going to mean it's going to be the biggest user. In the case of this, the 2, 3, and 4-inch meters represented 33% of the total meters in the system, but recorded 38% of the total use. Those meters obviously are critical in their system and to their revenues. Average age by meter side was conducted to provide information on meter degradation. Commercial meter test results, for the past 2 years were also examined together. This provided the validation to the 5% meter inaccuracy entered into the apparent loss area of the audit. Data handling errors are usually not a big issue, especially as we move to AMI, but things do happen, errors do occur. As we always say, what's a zero among friends? Everybody's had the story or been told the story about a drop zero, somebody missing a zero, and it makes a huge difference to billing 100,000 gallons versus 1,000,000 gallons. We also have the issues of meters not being billed. Did something not get recorded? Register heads not being properly programmed. In this day and age of technology, that's a big deal, and that can happen, and that can mess up your information you're getting from that water meter. With AMR, we went to mobile meter reading with efficient monthly data. We've moved into AMI with advanced metering. We have fixed networks. We're getting information on at least a daily, if not hourly basis on everybody's user. Now we're getting into the advanced metering and analytics. And with these powerful analytics, you can perform all kinds of information with two-way fixed networks, and you can be very proactive in what's happening in each of your customers and their systems and what's happening in their systems. reading averages, direct read meters. If you're still doing that, what is done a day is it goes through all this. You know how that's why FITS networks are becoming so popular, because you can read everything every day, 24 hours a day. AMI can help identify non-revenue water. It's an important tool in our apparent loss. Moving your system to AMI will help. It'll help increase your metered usage. It will help you control what's happening out there. An hourly metering data, you can see the difference. You can see system supplied versus non-revenue versus meter usage. Those are all important things, and how AMI can be very helpful. Test your meters. I can't emphasize that enough. I'm going to harp on that. I'll start with your production meters, your master meters. If we don't know they're accurate, our audit's completely invalid. And if we're not testing our commercial industrial complex, where most of our revenue is created, we're making a mistake. So test your meters. The effects of normal wear on meter accuracy is gradual. It will gradually slow down over time. It just doesn't quit all at once unless something jams in it. But if a meter wears over time, it just slows down. And in the table 5.2 M6, it lists testing frequency for every state, for regulations, testing by meter size. Just so you know, 16 states have no regulations. All that stuff doesn't really meet a sound business practice. After 35 years, I always use a rule of investing about 2% of your annual revenue in the maintenance or testing of that meter. And these are the averages that we use with our customers, and what we recommend to people who are doing testing programs across the U.S. This is the most cost effective, and we feel the best investment in your water meters, not based on size, not based on volume, based on money. Historical approach to meter replacement, the AWWA M6, any type of regulatory requirements, or we run to failure, or we did preventative based on age or consumption. With AMR and AMI projects, a lot of these are starting to be changed out because of them, which is a huge help. But we see over time and years, the payback time frame on changing out your meters, it really doesn't take long for the older the meter, to get your money back, usually less than 6 years. Make sure you follow the C700, the M6, the M32 or M33, and the M22 on the proper sizing of your meters. That's really important, because proper installation makes your meter last longer and run longer. And meters should be based on the following parameters: quality, performance, life cycle, maintenance, cost, warranty, manufacturer support, and a track record of historical performance. Just not because it's the coolest thing you saw on the shelf. And price alone should not be your final decision. Again, with your audit, understanding the chemistry of your water and the appropriate meter, and your associated maintenance costs, and do you have the manpower to handle it in-house. Real losses, the guys are going to jump into that, so I'm going to just pop through this on how important real losses are. In this case, water in this community is expensive. It adds up quickly when you're losing water, and by money or percentage, no matter, they've got ways to reduce leakage. I think you're all aware of that, from reducing pressure to running leak surveys, DMAs, shortening the response time of your repairs, and then maintaining your own infrastructure so you don't have tank overflows and other leakage. But the guys will get into those areas here. But as you see with the changing the audit, changing the numbers, we still had our real loss issue. So real loss tool helps you determine where your losses are occurring, what's happening to you, and why. and why that's so important to keep track of all that information and keep that information for yourself for your audit. So you need to conduct field work. So I appreciate everybody's time and attention. Hope it wasn't too boring or too dry. A lot of information all at once, but thank you for the opportunity to present. Don't know if there were any questions.
No, thank you, Mike. And yeah, we'll, if anybody has questions, just please put them through into the chat and or send an email following this, and we can always follow it up that way. It's just in the event of time here. So great. All right, good. Thanks again, Mike. Our next presentation, we're going to move right into, I'm going to share my screen here. And there we go. So we just had Mike. So now we're going to move into leak detection 101. And we're going to have Mr. Mike Ambrosiak share that. Let me just move this over. Is that correct now? Okay. Mr. Ambrosiak, are you able to unmute yourself? And there you go.
I'm unmuted.
Yep, you're ready to go. All right, and then I will handle, so just say next when you're ready to go, and take her away.
Okay. Well, thanks a lot, Noah, for the opportunity, and Mike Simpson. Great segue there to what I'm going to talk about here, which is just kind of the practices of doing leak detection in your system, the field work, as Mike put it. And yeah, I mean, as Mike put, you know, there's a lot of return on investment with these type programs that I think is sometimes hard for municipalities to wrap their heads around. But you know, investing in both staff and equipment will result in significant savings, both in non-revenue water, but also identifying leaks before they turn into major failures, causing social impact, economic impact, and sometimes even environmental impacts, depending on what part of the country you're in. So yeah, I mean, the investing in both doing an audit, as Mike mentioned, which is invaluable, and an accurate audit, and then getting equipment for doing, whether your own staff is doing it or whether you contract it out, is a critical part to eliminate or minimizing non-revenue water, and you know, getting as much water to your customers without losing it as possible. So yeah, if you want to click that home button there, Noah. So yeah, the two camps of leak detection that's out there is the annual survey contracted. So that's hiring somebody to come out. You know, there's companies out there that can do surveys, and whether you do, you know, specific parts of your system. You know, I know a lot of cities, you know, the bigger the system, the harder it is to get through all of it. But even doing, you know, select areas, you know, depending on age of your pipe, maybe age of the system, to help prioritize, you know, future repairs, replacements, rehabilitations, and then doing a leak detection program in-house where you actually have staff dedicated, which is essential. You know, having different crews trying to do a leak detection program, there's a lot of institutional knowledge that can get lost. But having a dedicated group that's managing a leak detection program can be very effective. So that first annual survey contracted, Noah. So again, hiring an external company, there's a number of them that provide this service. You know, different approaches can be done, walking the system, listening to valves, hydrants, and service connections. You know, this is a smaller initial investment than probably hiring staff and buying equipment. So it's a way you can kind of, you know, on an annual basis, get through certain parts of your system, and you know, maybe every 10 years you get through the entire system with this approach. And so, you know, the goal of this is to get through, you know, miles of pipe and hear leaks, and then, you know, deploy crews to address those leaks. But, you know, finding, you know, valve issues, service issues, and hydrant leaks, and occasionally you'll be able to pick up some leaks in the mains. And, You know, typically these are done during the day when the system is loudest, which is because during the day, usually in residential areas especially, the demand is lower, so your system will be, the pressure will be higher. You know, people are out working, so your pressure's higher, so those leaks will be more apparent during the day. So the other approach, Noah, if you want to go to that other bullet, I think if you back out with your mouse, or if you, there you go. So doing a leak detection program. So this is where you own the equipment in-house. You know, there's a number of companies, and if you were at ACE 2 weeks ago, there's many companies out there providing equipment these days. You know, just like as I tell people, cell phone technology is being used in the leak detection industry. So it's getting more and more user friendly, where you can use your cell phone even for managing your leak detection program. You know, tablets, you know, using technology is really starting to pick up in the industry for the equipment. You know, and when we do talk to clients about this and they say, well, you know, we're just having a hard time finding the budget for it. We don't have budget for it this year. You know, you don't need to start with $1 million, you know, equipment purchase. You can start with a equipment purchase that's that is commensurate with your you know, overall budget of your system, and start small and just start doing something. Because again, getting some staff and getting management bought in to do these type things is the biggest hurdle, I think, with a leak detection program. So with this type system, you know, you pick out quarter sections and you start, you know, using leak detection equipment, whether it's you know, ground sounding equipment, correlators, or loggers. You know, we'll talk about that in a couple slides here, but going through and identifying issues programmatically through your system. And, you know, the goal here is to identify non-surfacing leaks. And, you know, being in Arizona, I know most people say, oh, our leaks will all surface. We'll find our leaks because it'll surface. We got shallow pipes and we got dry soil, so they'll surface, which I can tell you on a number of surveys that I've done that is not always the case. It finds the path of least resistance. It'll travel down trench lines with, you know, adjacent sewers and make their way into the sewers. It'll find storm drains and work their way into storm drains. So that idea that it will surface is not always the case. And then, you know, being able to pinpoint leaks is another part that's critical in the you know, developing a program. So if you want to go to the next, there you go. So then the next aspect is just to cover in this leak detection 101 is leak noise basics. So there's three kind of points to make with finding leaks. So the first one is localizing them. And localizing is kind of that high level going out and localizing the water down to a specific area or zone. Which was kind of the things that Mike was mentioning. You know, when you are starting to develop a program or hiring a contractor to come out and do leak detection for you, you know, try to find the areas where you do have meter, you know, you have differential meter issues. And so you can go out and, you know, look at your meters and see where you have water loss issues and start in those areas. Or doing noise logging with loggers is another approach for that first step. So, you know, when people say, well, where do I start? My system's, you know, real big. How do I start? So the first one is to go out and localize specific quarter sections. You know, typically it's the older parts of town, but sometimes it's, you know, bad installation that causes leaks in your system. You want to go to the next one, Noah? So then locating, so locating the position of the leak. So once you've gone out and done a kind of a broad survey of a quarter section, for example, and you've identified some noise, utilizing correlators, you know, from basically, usually from valve to valve, you can put them on hydrants, air valves. You can even put them on meters in certain cases, especially in Arizona where our meters are outside the house and close to the main. And use correlating loggers to then identify where those leaks are in a section of pipe, typically, you know, 400 to 500 feet between correlators is acceptable depending on your pipe material. Certain pipes transmit noise better. And then pinpointing the leak, the last step in the leak noise basics. So prior to excavation and doing repair, using ground microphones and listening sticks to actually survey the ground where those correlators identified the leak to be, and really hone in on where the leak is before you start digging. And because again, the noise can, you know, with the correlators isn't always 100% accurate, despite what companies will tell you. There is, you know, sometimes challenges because of the way leak noises transmit through different pipe materials. So those are the kind of the basics of a leak detection program. The next step, so the theory of leak detection. So, you know, hearing the leak, utilizing equipment to achieve the best sound possible, and pinpointing the leak position. So, you know, basically noise in pipes, again, because of pipe material, because of pressure of pipe, because of backfill around the pipe, the noise that a leak creates can vary from one pipe to another, which again is the reason that I think a lot of cities are challenged to, you know, get staff to focus in on a leak detection program. And even with contractors, you know, it does, you know, take some proficiency, and there's some art to the science that comes in play when doing a leak detection survey. But again, as you go through the process and have either a program or a survey done, the more that's collected on your system, the more you know, educating you'll get on what your noises sound like. So if you want to click on that sources of noise, Noah. So again, there's a lot of ways these, you know, correlators and loggers can pick up noise. You know, of course, the best way is for finding leaks is actual leakage, partial obstruction of the pipe. So where your pipe has the jetting effect that Mike mentioned earlier, possibly by tuberculation or by reduction in diameter, consumption. So flows and meters, again, you know, when you do a survey with correlators or loggers, if consumption is going on, it can create some false positives. You know, with the correlators, you want to know where your services are, and either isolate those when you're doing a correlation or verify that they're not flowing when you're doing a correlation. With some of the logger technology out there, you typically want those to be set overnight when people aren't using their water, and have them collect the data, you know, in the 2 to 5 a.m. range, so that you're not getting false positives with meters. PRVs are another way that you can get noises in the pipe that can set off correlators or loggers. But again, having accurate GIS and having information, you know, in your contractor's hands or in your staff's hands with that will help minimize the amount of you know, false positives out there. Close proximity of a main to a sewer pipe. So again, the noises that a sewer pipe creates can also, you know, any noise, a lot of these, you know, hydrophone, you know, where they're surface mounted, can pick up outside noises from just the water running of a sewer pipe adjacent. You know, the change in pipe diameter, pumps. So, you know, when you are collecting data, you need to be aware of pumps in the area that can create a vibration and noise through the pipe, and you know, any outside noise can be a source. So again, it's the more you collect, the more surveys you do, whether it's your own staff or your contractor, the more you can eliminate these type things. But again, knowing that these things are out there is a critical piece of a leak detection program. Next bullet there, Noah. So yeah, how is a leak noise generated? So, you know, if you have a hole in the pipe somewhere, there's a mechanical vibration, and the louder and higher frequency leak noise is created by a large pressure differential between the water in the pipe and the area outside the pipe. And the mechanical vibration traveling throughout the pipe is the leak that we actually hear. So again, as I mentioned, depending on the size of a leak or whether it's a joint leaking, and then even the backfill around the pipe will impact how that noise is generated. And as I mentioned, a lot of technology and algorithms are in place with a lot of the technologies out there to help filter through this type information and provide more accurate data with different type pieces of equipment, whether it's loggers, correlators, to identify where the leak is at specifically. Next one, Noah. So again, the backfill, as I mentioned, so if you have, your pipe is in a loose, soft backfill, the water drains away. So there's a high pressure inside the pipe and a low pressure outside the pipe because that backfill is looser, and so that'll create a good noise for your pipe. And then the next slide shows, if you have a more compact clay backfill, the water can fill that cavity and create less of a noise when that occurs. And again, the technologies that are out there and evolving very quickly are trying to help with these type different situations. But things to keep in mind when developing a program, and again, bearing in mind that doing leak detection is not a 100% certainty all the time, but the thing you got to remember is when you do find leaks, it is saving you money. It's preventing a failure down the road, and the return on the investment will be realized and should be calculated when you are doing these things, so that you can show management and city council and the accountants in your system that this type program is a huge cost savings when implemented properly. Next one, Noah. So then even the type of break in your pipe or the type of leak. So obviously a large burst, if that happens, you lose pressure. So that's something that you can keep an eye on. And as Mike mentioned, even managing the pressure in your system is a good way to reduce the amount of leaks you have. So making sure that your pressure reducing valves are working properly is a big impact to the life of your pipe. If your pressures are, and I know, even in my neighborhood where I live, we have pressures exceeding 120 psi, and it's something that if you can avoid high pressures, even though that pipe's rated for 150 a lot of times, the closer you can keep it to 50, 60 psi, the better the life of that pipe. So again, but what happens with large failures or large leaks is that the noise isn't as high, the frequency of that noise isn't as high, and sometimes can be difficult to hear depending on the sensitivity of your hydrophones. Next one. So then with a smaller pipe rupture, less pressure loss, but these typically are louder and higher frequency. The other place we see the smaller, whether it's a rupture or even at joints, usually joints have a higher frequency, and the noise is much more apparent with the correlator and the logger technologies. Next one, Noah. So just to summarize, the factors affecting good and poor leak noise to keep in mind when you're doing a program is, good quality leak noise is, the higher water pressure, porous backfill, the smaller holes or joint leaks, the cleaner pipes, because again, the thing to remember there is that if you do have a lot of tuberculation and buildup, the noise is harder to transmit through the pipe. There's more items to kind of deaden the noise as it goes through for picking it up with the hydrophones. And then smaller diameter pipes, your distribution pipes, the technology that's out there is better for smaller diameter. And then pretty much down the line is the opposite for poor leak noise. You know, not to say there isn't large diameter. Usually the large diameters, though, you want something in the water column to do leak detection. Next one, Noah. And then pipe material. Any leak detection person will tell you plastic pipes, you need to have your sensors closer together. And that's simply because noise doesn't travel as far in your flexible pipe materials as it does in your more rigid materials. So steel and ductile, copper and AC, noise travels pretty well down those. Your plastic materials, it's harder. And basically, you know, in those situations, you just need your loggers and correlators closer together. Next one, Noah. So your leak frequencies, again, something to keep in mind, which, you know, when you're using correlators, you see this information when you're collecting the data. So just, you know, keeping this in mind. You know, one thing that we do see when we're doing some of these surveys is when there are, you know, metallic pipes that have PVC repair fittings in or repair sections in from previous failures, can impact your frequency when you're collecting your data. So just something to keep in mind when you are collecting data, to verify what your pipe material is with this frequency information that most of these correlators collect when they're collecting leak detection data. So the leak noise quality, again, important factors to keep in mind is the clarity and strength of your actual, so according to what your pipe material is and the pipe condition internally. So, you know, some good leak noise where filters are not normally required. They're clear, and we'll show this in some slides coming up here, just what the peaks look like when you're getting a good leak noise. And again, this is the stuff where, you know, the more you utilize your equipment and or your contractor that's doing this, the more experience they have with this, the better they understand what good noises look like and what poor leak noises look like according to your frequency curves that come up. So again, just kind of a summary of the factors impacting leak noise. You know, keeping in mind material, pipe diameter, and pressure, all things to keep in mind when you're doing a leak detection survey. Background noise, making sure that you get those minimized as much as possible. And then even, you know, the consumption. So, you know, doing surveys when services aren't being used, with loggers collecting data when it's low demand type times of the day. Go ahead, Noah. So correlation, so when you're doing a correlation, as I mentioned, there's correlators, which basically are surface mount sensors. So as you can see, the graph on the left with the peak, that's a good sign. And like I said, most of the equipment nowadays have visual outputs when they do a correlation that show you the peak there and help identify, okay, that is a good noise, versus you know, dissimilar sounds, which basically give you a continuous noise from one correlator to another. You know, again, ways to minimize those dissimilar sounds is to reduce the distance between your correlators if possible. And then even, you know, if you do have places where you don't have a real good peak, using ground sounding equipment to verify if there is a leak in that section of pipe. Go ahead, Noah. So when you're correlating, you know, you want to locate all the possible areas for access points. So like I said, hydrants, valve operator nuts, you know, even meters in some cases where you have access to the water main. You know, again, some of the things that go into this is, you know, cleaning out valve boxes so that you have good connection to that metallic part of the pipe with your sensor. Listening at the access points using, you know, acoustic microphones, and then, you know, the measurement area, making sure accuracy is of the distance is important. So when you do a correlation, With correlators, you want to know the distance from one correlator to another. And, using a wheel is a minimum, but one of the challenges we have with water mains is geometry changes, both vertical and horizontal, that can impact that distance. So that's something to keep in mind, whether you're using loggers or correlators, of trying to estimate what your distance is from one access point to another as accurately as possible. And then, again, making sure you have good connection to your pipe. So your on-site setup, just kind of a schematic here of what it would look like. You have your two correlators, A and B, and you have a leak noise correlator. And basically, you run your correlation. Typically, I like to, if you do pick up a leak, you like to run it a couple times. Typically, the correlation takes, 2 to 3 minutes for the two sensors to correlate. And, with most of these correlators, they have antennas that then sit on top of the valve box there, or sit on the surface level, so that leak noise correlator can communicate with both. Go ahead, Noah. So as I mentioned earlier a little bit, sensor positioning, you want to try to make it, try to pinpoint that leak as good as possible with your correlators before you start using your ground sounder. So if you are able, if you do hear a leak, between two valve boxes or two pertinences, trying to get them as centrally located as possible so that you can pinpoint that leak before you start ground sounding. Again, the correlators do give you distances, though, of where your leak is from A to B, or from A and then from B, and you can use that information to then go out and use ground sounding to verify and before you start excavating. So again, with the sensor positioning, second correlation. So on this application, there's probably, this is looking at if you had a meter or a lateral between your two sensors, you can move that sensor, somewhere closer to that correlator B, and verify exactly where that is. So again, if you have other places you can put your sensor that would minimize the distance between A and B, that is also ideal for doing a survey with correlators. Go ahead, Noah. So just the kind of the input you would do when you're using a correlator or correlator system. So this is the screenshot of a noise correlator dashboard. Usually they're on tablets, or sometimes they have their own communication box. But inputting your material, your pipe material. This is in metric, but we can get that adjusted to inches as well. Your length, so your length between the two systems, and then the velocity is a measurement that is according to what your pipe material is. So that's the basic of it. And then interpreting the results once you do your correlation. So the top leak is within the spread of the peak there. The bottom one is one more that Manhattan skyline, where you'd want to try to either minimize the distance between your correlators or your loggers, or at this point you probably would want to do some ground sounding to verify those noises that you hear at that point there, somewhere in the middle. So then small velocity errors will cause correlations in the outer thirds to be less accurate. So again, if your leak isn't really in that middle third with the correlators, before you start digging, you probably want to verify, and again, either get your correlators closer together to really get that leak to be in the middle portion, or do ground sounding if it was outside those two places to verify whether you can hear a leak at the ground level. Go ahead, Noah. So again, just a screenshot of what the ideal position is. When your correlators are picking up a noise, and you want to try to get it as center as possible. But with this type situation, the velocity of that noise has little effect as the time delay is small when you're doing a correlation in that respect. So just some example correlations. Poor leak noise is, as again, you have a lot of noises across the entire pipe there, which could be a variety of reasons. It could be that your pipe has a lot of tuberculation. It could be a lot of outside noise that's causing those. So, different things can impact it. And again, it's part of that art to the science of doing leak detection surveys. When you do get data like this, knowing how to mitigate that, whether it's putting your correlators closer together or evaluating your pipe material and figuring out whether it's a good correlation or not. The other point to make here is in the top right, there's a Q percentage there. So that's basically the quality of the data. So that's the algorithm. Basically, the two sensors or the two correlators verify with each other what confidence percentage they have. And typically, when we do a correlation, if it's not 85% or higher, we usually are not going to recommend starting to dig yet. So just something to keep in mind and a good tool to have when you're doing a correlation. Go ahead, Noah. So just to briefly go over the equipment, so the acoustic microphone where you're doing the ground sounding, an elephant's foot, if you're doing it on a solid surface, there's other sensors that are better for softer area where you have decomposed granite or just a soil backfill and no paving. Can also be used on valve leaks, and is a good initial investment for doing leaks, even for when if your crews are out even doing repairs on surface leaks. Going out with acoustic microphones is a good idea to help pinpoint exactly where that leak is occurring. Go ahead, Noah. So the correlators, as we just went through, used to, when you are out doing a survey, you put A and B on adjacent valve boxes or services, hydrants, and this really helps collect good data to minimize the amount of chasing you're doing. And it uses acoustic frequency data and transmits via radio, so it's all right there in that system there. You don't have to use any computer software or even any sort of equipment. So then the radio loggers, so these are ones that you set out, leave them overnight, and it collects data. Typically you want to collect data between 2 and 5 a.m. when you want these to listen. And again, historically loggers used to just identify noise and then you'd have to go out and pinpoint them. Nowadays there are correlating radio loggers that actually do the correlation as well for you, and actually send the data. Well, you go out and collect the data with a tablet, and it puts it onto a cloud so that you can actually do the analysis of the data at a computer in your office later. So full correlation, a lot of words here, too many words actually, but basically a full correlation is all the loggers are synchronized, so they all are working in unison and listen together, and then it correlates pairs every day. So adjacent, when you set out 10 loggers, let's say in a mile stretch, they all correlate together, and then there's algorithms in the central server that trigger the leak alerts by system. All the data that the loggers have ever collected and transmitted remains stored centrally identified for full historical analysis and benchmarking. So you get basically a GIS output that you can overlay into your GIS and use for historical tracking and benchmarking. And then so that the question of can I still find leaks without fully correlating, the answer is yes. but the correlating loggers are good in that you can deploy them with minimal staff. They can collect a lot of data in a short amount of time. You know, clients that we talk to about using correlating loggers, you know, if they make an investment of, let's say, 50 loggers, you know, staff can go out, set them on Monday, pick them up Tuesday, reset them, and continually get through entire quarter sections in a couple days. So, you know, can you do, you know, leak detection with just the basic correlators and just ground sounding? Absolutely, but the best bang for your buck is, and I, you know, even when we go out and do some surveys, even if it is just one specific area that a client wants to look at, setting 5 or 6 loggers makes me feel better because we can collect more data and verify exactly where that leak is with with multiple correlators working in unison all at once. Go ahead, Noah. So what is a correlating logger here that a standard logger can't? So what the correlating logger is, the nice thing about it is it will trigger to turn on at whatever interval you want in a period of time. So usually it's a 2 to 3 hour window, and they turn on every 20 minutes. And so what that does is, if there isn't continuous noise being heard, i.e. someone turning on their, you know, using their faucet and, you know, noises that are not continuous will be eliminated in the algorithm when it does the filtering and identifying of leaks. So the correlating loggers are nice in that it's not just an instantaneous. So permanent monitoring, very similar. You set up loggers, you permanently install radios. So in areas where you have, you know, either high profile pipelines, you know, a lot of these are set up underneath busy roadways, you know, cities that have, you know, high density traffic areas and places where pipes are really critical, low redundancy. Setting up permanent monitoring is a great idea. It'll you know, listen every night for you. It'll send out alerts if it does hear a leak. And you know, for areas of town that are high profile, doing a permanent system is available and really advisable to minimize catastrophic failures. So Mike talked about a lot of this, but you know, identifying non-revenue water. So you know, a lot of stats here that Mike talked about a little bit, but you know, there's a lot of studies that have been done in the last 10 years talking about the amount of water loss due to leaking pipes. You know, distribution systems, you know, have quite a bit of leakage every day, some up to 50%, and you know, identifying and mitigating those is critical using a leak detection program. So you know, the average loss according to the EPA in 2013 was up, and up to 75% is recoverable if you have an accurate leak detection program. Go ahead, Noah. So Mike talked about a lot of this. I'm not going to go through all this, but real losses versus apparent losses. Same, you know, very similar. Well, this is the exact chart that Mike showed earlier. So to just identifying what those authorized consumptions versus unauthorized consumptions. I mean, I was just on a construction site today, and they're doing repair of a pipeline, but the closed valves are probably allowing somewhere between 50 and 100 gallons a minute of water loss right now. And because of that, and I'm sure nobody's metering it. So there's a lot of those type things that go on in a system when they're doing maintenance that aren't really metered and aren't being accounted for when you're doing your audit. So again, Mike talked out a bit on this, but you know, the using AWWA standards to really calculate apparent losses and real losses versus your gallons per service connection per day. Go ahead, Noah. So, you know, the solutions that are out there controlling apparent losses using, you know, by accurately measuring meters, systematic data handling errors, you know, the missing zero that Mike mentioned, unauthorized consumption, which has a variety of hats, and then controlling your real losses, which is mitigating leak control, pressure management, and then water main rehab and rehabilitation. So using your leak detection data to then prioritize where you should be rehabbing and replacing your pipes. Go ahead, Noah.
Hey, Mike, just in the interest of time so that we can give Eric time, are there things, do you have enough to wrap up here in a couple minutes?
No, I think I'm just about done here, Noah.
Okay, good.
Yeah, so you know, the goals of a program is getting equipment that works for your system that makes sense. You know, if you've got your crews doing it, maximizing their efficiency by using equipment that uses as few staff members as possible. And then as you find leaks, pinpointing them, decreasing water loss, and increasing revenue, which again is all of that overarching theme that Mike talked about of this is real dollars that we're talking about. And if you can minimize leaks, you're going to save a lot of money down the road. So creating an effective program, again, you know, getting staff engaged, getting management engaged, and developing a program that collects historical data so that you're not just doing snapshots, but that you're comparing from one year to another and collecting data that will be useful for, you know, the next generation of water operators out there, which is available. You know, with a lot of these cloud-based systems, you can collect the data and it'll be there forever. And you can compare from one year to another what your leaks were in your system. I think that's it, Noah. Yeah, I mean, the return on investment, you can.
Yeah, no, and I think you're right. We had a good amount of this stuff.
A lot of stuff that Mike talked about already. But again, leak detection programs should definitely be looked at. You know, I know that there isn't a lot of state requirements right now for it, but even starting small with a program and getting staff engagement will be beneficial for you know, the dollars at the end of the day for your water system. So
yes, sir.
I appreciate it. Thanks for your time, and yeah, we'll let questions at the end there if people have them in the chat room.
Yep, awesome. All right, thanks again, Mike. And we're going to move right into Eric Dole because I know Eric has something he has to get on the road for. So I'm going to switch the presentation. Eric is going to talk about embedded energy lost in a distribution system leaks, find them, fix them, prevent them, and save money. He's with Hazen and Sawyer, and it should be on you, Eric. Go ahead if you can.
All right. So I think I just clicked on the button, so you should be seeing this here.
Yep.
Let me know.
Just do the full screen and then we're set. I see it.
All right, cool. All right, everyone, I'm going to try to step through this presentation. A lot of it kind of springboards off of what the previous presenters, Mike and both the Mikes, talked about with different technologies out there. A lot of it may be reiterative here, but we added a couple of things to this presentation where we actually look at satellite leak detection technology, and Mike Ambrosiak mentioned the continuous correlating technology, and that's the two leak detection technology we really honed in on that's attached to the embedded energy. So I'm going to get through this, and here's a brief agenda. We're going to talk about the project, the technologies, systems evaluated, the embedded energy, what is that, how do we calculate it, what does it mean, and then the water energy savings to date, and by that it's about the past 6 months is where we had some really good data and water saved. Observations, some unintended consequences, and some things we noticed along the way that you know, kind of lends itself to not just find them and fix them, but prevent them. And then future work. Let's face it, aging infrastructure, leaking pipes happens all over the place. When do you replace them? Could go years before it comes to the surface, could leak a significant amount of money. But like the previous presenter said, when do you actually fix it? When does it make sense to? You can't go in the middle of a busy intersection to fix a 1 GPM or a half a GPM leak. But we're going to talk about the cost to make the water and when does it make sense to replace it, and what can we use for drivers to help push a pipe replacement. Basically, leaks equals lost water, infrastructure damage, and lost water equals lost energy, the way the California Energy Commission sees it, and that's why they funded the project. Here's a brief org chart of who did this project, funded by California Energy Commission, and it's a partnership between Hazen and Sawyer and California and American Water. where I was the co-investigator and the project manager in charge of or at the time in charge of the embedded energy calculations. Had a pretty good support team here as well. So the goals were to deploy, evaluate, and improve the following technologies you can see before with the acronyms. There's CCAM, which is continuous correlated acoustic monitoring, satellite imagery, leak detection, and flow sensitive pressure reducing valves, more of a pressure management technique. It's not to say who's better than the other, but more of what can we do to make it better for market deployment out here in the United States. All right, I'm going to evaluate the financial characteristics of this project. Present potential energy savings and greenhouse gas reduction to date, plus water loss. And of course, energy just compounds the water loss problem for utilities. And of course, it can be used for a metric to help decide when to pull the trigger on a program, when to replace a pipe. So these are the four major metrics we look at leakage. What we're going to focus on here are these two: pressure management and proactive leak detection. Basically, subsurface, non-invasive leak detection. And that's why CEC sponsored this, so we can figure out what is the actual lost energy associated with lost water. Here's a quick breakdown of the various systems we looked at. The technology on the left, the trade name, we got Ecologics, Utilis, and Stream Control. Utilis and Stream Control out of Israel. Ecologics is here, they were bought by Mueller. Some of the goals of the different technologies and where we deployed the system. So there's three systems that California America offered up to us. There's Duarte in East LA, Ventura in East LA, and then Coronado down in Imperial Beach, just at the very tip of California. The ecologic sensors is the continuous correlating acoustic monitoring, and that's where, just like Mike had mentioned before, it's continually, it measures when you get a pop in the acoustic signature in the leak. Some can be used on both dry and wet barrel hydrants, which is good for cold environments as well. PVC, as he had mentioned before too, they have a very different sound signature, acoustic signature with the pipe material. PVC will require more sensors, and actually Stream Control is deploying a sensor right now that is a little more sensitive. We have not been able to test it, nor will it be available by the end of this project, but that may be in the next phases. This is the signature you typically see. Sometimes you have to, it's hard, if you're in a high traffic area in the middle of the day, it's hard to pinpoint a noise versus it could be a pump or it could be an airlock pipe. Sometimes air makes a big signature. It can really skew what's going on in the frequency, which also tells you a lot of other good things. If they can pinpoint where air is, that could tell you to get the air out of the pipe with an air valve. And what they do is they take this data, they scrub it, and they develop a bunch of point of interest. That sends us out locations where between the hydrants this potential leak could be. Then we have to send out the field correlating techniques, which is exactly what Mike talked about before. I'll have a slide to just touch on that. The other technology is the SILD by Utilis. And that actually takes microwave-based technology and covers a large geographical area, and it can pinpoint chlorinated water subsurface, which is pretty cool, pretty nifty. It has corrective algorithms to locate and find suspects, and you can get them as a one-time scan monthly or quarterly. It does have a large POI radius, point of interest radius, about 165, so it's more of a gross swipe of the area to see where these potential ones are, whereas the ecologic system is more pinpointed between two hydrants on a barrel of pipe. This is a typical correlation map we get of the Duarte system. You can see the green nodes are the ecologic sensors, and the red circles are pops of points of interest for the Utilis one, with the shaded ones being the higher frequency. So then we can go and compare and see how it matches to the Utilis or to the ecologic system and vice versa. What we need to do with the point of interest, once we have it, they shortlist it, and they give us a map of which ones our field crew needs to go out there and go ahead and correlate it either with listening sticks or devices, field correlations, the purposes, sensors you put on the actual valves and the hydrants. At first took a good amount of training, and like one of Mike Simpson had mentioned before, if you have leak detection technology folks out there, try to keep it the same folks so they can really hone their skills and get good at it, and just dedicate a section of the field staff to get out there and go after it, because they tend to get really good at it, and now they're kind of jazzed up about the process, and they're good with it. These are what they look like that we use for the for the field correlation once we have a point of interest, anywhere from $30,000 to $40,000. It requires transmitters, headphones, listening sticks, and a laptop computer, basically. So summary to date on the leak detection is that utilists and ecologists are finding leaks. Utilists about a 75% hit rate, and ecologists around 30-35. But note that utilists has a much larger point of interest, so it's not really an apples and apples comparison. Both systems are capable of identifying missed leaks by the other system, whereas both of them can find leaks that the others did not find, and sometimes they're correlated. So there are opportunities for both systems to analyze, perform, take corrective action, to modify their system and make it better. I mentioned before, Ecologics is looking into the PVC sensors, whereas Utilis tends to have some issues when there's some topography in the area. If it's on a hillside, it has to have some triangulation calculations that are easy to blow. So they're trying to figure out how to fix that, and they're doing a good job. It's actually come together quite nicely. You can do more flyovers also. So the conventional leak detection is just district metering. You heard the DMA acronym thrown up there before. That's just typically where either at pump stations or PRV vaults that we have flow monitoring, and we also have pressure. And what you want to do is just catch potential unauthorized use, anomalies, and diurnal trends. And if you couple with pressure, it tends to tell a lot more of the picture. Here, the blue line is the pressure, and the red line is the flow. And what this tells us is an excessive pressure event caused an increase in flow through a meter, which is likely a pipe break. And you can see here's where they fixed the pipe leak, and here's where leaks continued. Another one we're doing for more of a pressure management we're evaluating is this AquaGuard system by string control. It's a FSPRV, flow sensitive pressure reducing valve. And the whole concept here is that there's less head loss at night due to friction loss. So in the middle of the night, you have less flow, you have less pipe fluid velocity, less friction loss. So a 40 psi residual pressure at a PRV vault can be dumped to maybe 30 psi, and you'll still satisfy a pressure requirement and a remote part in the system because there's less friction loss in the pipe to get to that node. So what they do is this is a smart flow sensitive PRV. You can see on the right hand side here, there's an FBI insertion meter, and it detects when there's a prolonged period of low flow and pops it into a AquaGuard takeover of the pilot system. And this goes on any PRV, whether it's a Vermad, a clay valve, you name it, it can go on any PRV. And what it does is it dumps the downstream pressure setting to whatever you want it to be, 10, 5, 15 psi, just to reduce the barrel of the stress on the barrel of the pipe, and either decrease leaks or reduce the amount of leaks. In a high flow event, it deactivates and it goes back like it was never in there unless the hydraulic pilot take over. Schematically, this is what we're looking at here. Most PRVs, you have a high flow and a low flow PRV vault. This goes on the low flow PRV, which tends to be the higher pressure setting. The other parallel high flow PRV, the bigger one, is set at the lower pressure setting, whereas at the smaller PRV can't keep up and the pressure keeps dropping, and then the big boy opens up, and we don't care about that one because we don't want to decrease pressure at that point. There's some event that needs to be consistent. It's typically the low flow nighttime PRV, it takes over. And what happens is it works well when you're floating a system off the tank hydraulic grate. And you'll see here there's a pico turbine or a small turbine here. That's required because most PRVs do not have power, and this thing does require power. So you can either put a solar system in there, and here we decided to put in a small clay valve X143 generator to provide the power and charge the batteries for the AquaGuard system. Pretty unique system. The project, like I mentioned, there's 3 distribution systems we looked at. One was the Duarte system, supplied about 100% wells with inline boosting, several pressure zones, 100 miles of steel, asbestos, and plastic pipe. There were 87 main breaks in 2016 and 140 in 2017. We deployed the Ecologics and Utilis technology here because we knew there was a high water loss, a lot of pressure issues. Let's throw this out here and find them before they become an issue. And this one was a candidate for embedded energy calculation. The other one was the Ventura District. It was 100% supplied by the Metropolitan Water System via Callegas Water, so it was a pass-through system of Callegas. They service this. They have all these different turnouts you see in blue, and that feeds the system where then they repump and distribute amongst their system. Specifically, the Dos Vientos PRV was what we used, what we looked at for the Ventura District. So they have corrosive soils, hilly topography, plastic NAC pipe, a lot of service line breaks due to polybutylene, the poor polybutylene collection, and some copper. We did a flyover with the SILD technology, and we deployed the AquaGuard system here and district metering to see how if we can notice a difference between before and after we implemented the PRV, pressure management through the PRV. There was, as we mentioned, it's about a little over $1 million research project, so we had limited funding for where we can throw all the different technologies. We decided to just look at SILD and AquaGuard here. It was about 30 to 600 GPM on a typical day. This is the different PRVs feeding the zone. This is what it looks like with the AquaGuard system in there and the generator with the battery and the controller. This one was not in the candidate for embedded energy calculation because one, they didn't have the good records to match up with flow monitoring, so we couldn't waste too much time. The Duarte system was more. You'll see I have a checklist for what makes it a candidate later on, so I'll get into that. The Coronado system was 100% fed by gravity the whole way from the city of San Diego to Otay Zone. There's zero net energy in Coronado system to distribute the potable water. And what they're kind of doing right now is kind of neat outside of this project, but they're going to be putting in a 500 kW turbine that recovers all of the throttle head from their pressure sustaining valve or fill valve that's going to now spin a turbine and throw energy to the grid. There's not a significant leak history here, but again, it's in San Diego on the beach and there's sandy soil, so who knows if there's a significant leak history. The only thing that could tell them, which they haven't done yet, would be a water audit where they can look at the non-revenue water between what's going out in the field and being billed versus what's distributed at the sites. This one as well was not a candidate for embedded energy because they did not spend any energy to make the water. So what is embedded energy? It's basically the energy used to pump and treat the water in kilowatt hours per million gallons pumped and treated. It's otherwise known as energy intensity. And the reason why there's two forms of energy intensity. There's kWh per million gallons a day, which is demand-focused energy intensity. There's also it's a consumptive energy intensity. Demand-focused energy intensity is a kW per MGD. These are, you tend to get rebates on this from utilities that are just incentivizing on kW saved and not kilowatt hour saved. Noah can speak to that a lot when we work with what he's doing right now too. Lost water is lost energy and relies on technologies to find the leaks, estimated volume of the leaking water, and historical trend of kWh per million gallons a day. And a little fun fact here from AWWA M36 is that an average service flow leak flows about 6.6 gallons a minute and could last anywhere from 60 to 100 days. Mainline breaks are obviously a little bit higher in flow and shorter in duration because they tend to surface quicker. Talking about energy intensity, Coronado and Ventura. City of San Diego and Metropolitan come up with this cool table here, which is in the Urban Water Master Plan, where they come up with a kilowatt hour per million gallon day already, just so we can compare what we've seen with Duarte to these bookends here. The reason why Metropolitan is so much more kWh per million gallons than San Diego is because they have to get over the Tehachapi Mountains. Consider a lot of pumping there. So here's our checklist. Got to have a good electrical and/or treatment costs to the customers and good historical records of these costs. So if you're pumping and treating the water in your system and not relying on somebody giving it to you, that tends to be one of the boxes you want to check. And you have to have good historical records of the kWh and kW. You need to change the SCADA dating, total flow polling, to match the electrical billing cycle, get a true kWh. You'd be surprised at how skewed your data can get if you have your polling data, say the electric utility bills on the 5th of each month, but your total polling data goes from the 20th to the 20th, was to change the scope, the total flow polling to match the electrical billing cycle. So we got a really good kWh per MG. And on top of it, you need to deploy a non-invasive subsurface leak detection that geographically detects the leaks with a good accuracy prior to surfacing. So that way you can pinpoint the leak when you found it, verify it, expose it, get a good gallon per minute reading, and then the next step is we'll talk about here is what the flow duration is. Does the system have to have a significant history of non-revenue water leaks? It helps, but not necessarily all the time, because as we mentioned before, if you have sandy soil, it could you could be having a significant amount of leakage and not know it. That was Duarte. So we can do two ways to do embedded energy, and one's with extended period hydraulic simulation. We perform a tracer study, so we can allocate the percent kilowatt hours per million gallons from each of the various well pumps in the system and figure out what percent of a drop of water comes from each of those sources. That costs a lot of money, a lot of time. We didn't have that, so we said, what's the next thing we should do is just let's take the total kilowatt hours per million gallons from all the well pumps and flow rate it as a percentage to get a gross aggregate 2464 kilowatt hour per million gallons. Couple in the kWh from the boosters that did not have flow meters, just tack it on to the kWh of the well pumps. And that was our one energy intensity metric number used for the Duarte system. So any leak that we had, we would multiply the total million gallons a day estimated leaked into the system that we found times this 2464 to get a kilowatt hour saved. Now, what is this bookend here? This is for AWA M36, and our research team decided let's put in some bookends here. So anything less than 10 GPM, we said was going to be between 60 and 80 beats. The flow duration, 10 to 30, was 10 to 60, and so forth. Anything over 60 was going to surface pretty quickly. It's a best guess based on a lot of different things that you can see there. And a lot of technical papers, including M36, is it could last for weeks, months, and years. So where are we today? What we found is that we've saved about, between 145 and 137 million gallons at a tune to a little 100 to over 300,000 kilowatt hours saved, and between $26,000 to $81,000, considering they're paying 24 cents a kilowatt hour over there. That's about anywhere from 7 to 22% of their total electric costs from 2017. How many pounds of CO2 did we reduce? About 58,000 to 177,000 pounds of CO2, according to the EIA.gov electricity website. A couple of things we noticed along the way. We talked about finding leaks, and this is preventing them. Every single one of their well pumps that they have sand separators on did not have air release valves at the intermediate high point. This was validated by cloudy water downstream of this system and a lot of pressure transients. So what happens is that pipe airlocked through the air bubble through the system and cause a water hammer that would then exacerbate the pressure on the pipe and break it. In the meantime, it would also airlock the pipe and hydraulically choke it, so the well pump was operating harder than it needed to. We said, let's put some air release valves in there. It costs about $200. Another one here is on the right-hand side. These are all product lubricated vertical turbine well pumps that use the distribution system water to lubricate the shaft. There was no automated solenoid valve system that would open on a call to run, fill up the column shaft, time out, close, and then let the well pump go to town and then turn off. This one just constantly bled about 13 gallons per minute around the check valve down the hole for 3 well pumps. And that was about 21 million gallons a year that we figured were sent back down the well pump shaft through this 3/4 inch line. Future work efforts, let's look at low closed loop pressure for pump station pressure set point depression. That's basically where you have a closed loop system and you can dump the system pressure at night and turn off pumps and reduce the barrel stress on the pipe. That kind of looks like in a system like this. So in Arizona, we love to fill tanks, break head, and pump the closed loop system because we don't have the luxury of elevated tanks. And if you have a closed loop pressure distribution system, this is something you can evaluate as a low cost solution here. Key performance indicators, things that we're looking at, dashboarding, develop, instead of having a lot of forms for them to fill out, make it on a laptop or make it on the, iPad that you can just run this on and put all the interface, all the inputs in there, and it can automatically populate up to the main dashboard, and it can depict how many kilowatt hours per million gallons saved, number of leaks, so forth and so on, and give you a true dashboard that you can see how well you're doing, the fitness of your system. With that, I'm done. Acknowledgements. There's a ton of people I'd like to thank for this project. Starting with Dave Hughes, he was the original American Water PM on the project, recently, and Ben Stanford and Kevin Moore and so forth. But it's a fun project. We're going to have a report out here by November, December timeframe. And if there's any questions, I have to go right now, but you're more than welcome to give me a call. This is my cell phone and my email. If you have any questions, I'd love to try to help. And with that, Noah, thank you very much for giving me that opportunity.
Yeah. No, thank you so much, Eric. I know you got to run, but this has been great. And really appreciate everybody else's time here. And, we're going to end it there. So just want to thank you all. This has been a great presentation on water loss termination and management programs. Any questions that the audience may have, I would suggest we just email them. We have a cap of 2 hours here on the webinars through the AZ Waters GoToWebinar, so it's going to end shortly. So just feel free to send an email to me, at which point I can put us all in contact with both Mike Simpson, Mike Ambrosiak, and Eric Dole. We plan to make available a copy of each of these presentations as a PDF if we can, or at least please visit the Energy Management and Sustainability Committee downloads webpage in a few days, and you can see that, and or the video recording of this should be up. The AZ Water Association has many interesting events planned for the future. Many of these events are free, and some of the events take place, such as plant tours or workshops, may include free breakfast or lunch. Hooray. Please visit the AZ Water Association's website and check out the event calendar for details about these events. And as a other follow-up, this is the second of what I hope to be a 4-part series that we will eventually be doing quarterly, trying to transition some webinar usage for the AZ Water membership related to energy, water, and of course, then going back into leakage and that. So with that, just want to say thanks to everybody for being on, and look forward to any feedback and also seeing you all in the next one.
Thanks.
All right, guys. Bye-bye.
Have a good one.